Well, I'm proud of you guys. You have gotten really through all of our derivative rules and ways to analyze a function using derivatives. So now we're going to spend the next couple classes looking at how all of these will help us actually analyze some somewhat real-world situations. This is kind of a sad lesson, I think, for AP Calculus. We are still, of course, in the middle of our topic for applications of derivatives, AP Calculus AB. Um, but it's kind of a sad one because ultimately calculus really should be focused on ways we can use this in the real world. And I think the AP exam has done kind of a poor job here, and they've really cut down a lot of real world optimization questions. So some of you guys might be saying, yes, we don't have to do real world, it's more straightforward. And in one way, you're right, but in another way, it's nice to see how we can apply calculus to the real world. So although we're only going to spend a day on this, and optimization problems have really shrunk down to maybe one question, or ultimately it might be 0 questions, and you might put this under the category of the candidates test. Speaking of missing a parenthesis, but yeah, I don't know. It's kind of a weird lesson for me. So let's get into this, and I'll try to explain more of what I mean by kind of a sad time for optimization as we go through. So when you want to optimize a quantity, and a quantity could be anything you want. It could be a characteristic about an equation, like concavity that we're about to see. It could be the amount of money you make. It could be speed. It could be really anything. When we say optimize, we're really looking for the absolute max or min of that quantity, right? What's the fastest speed that this car can go? What is the optimal gas mileage? What is the this? What is the that? And usually what happens is you're given some sort of an equation that describes a real world situation. And then there are a whole bunch of constraints put on that equation. You see this a lot in pre-calculus too. They're like, well, you can only go this fast, but you also have to stay under this amount of gas mileage and blah, 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 and you have all these constraints you have to take into account. Well, calculus has a really elegant way of doing that by actually taking the constraints, combining them into our original equation, and then using derivatives to determine the maximum or minimum, right? What we're going to do is a few steps, and you've actually already done all of these steps before. You actually are going to have done all of our calculus steps every time before for the rest of this semester. You've learned all you need for derivatives. Now we're just applying them. Well, let's get to it. So step 1 is state or create the function you want to maximize or minimize. Step 2 is take the derivative of that function. It's calculus after all. If you are not citing a theorem, taking a derivative, or doing a limit, you're doing the problem wrong. There's no other option there. You'll need to find the critical points, and then you'll need to perform the candidates test. Sometimes you can get by with what's known as the lonely critical point theorem, and we'll address that in this problem as well. But the candidates test, if you remember, is where we test both the endpoints and the critical points, and we test them in the original equation to see which value is the largest versus which one is the smallest. So let's rock and roll. We're going to start with a probably non-real world application and more just discuss a characteristic of an equation. So our goal is to find the most negative concavity that occurs on f of x equals that weird equation over the interval -5 to 5. Well, the first step is state or create the function you want to maximize or minimize. I don't want to maximize or minimize this equation. That would be what is the most negative or most positive value. If I want the concavity, the value of the concavity, then I need my concavity equation, which means a couple derivatives, right? And I'm going to write them out 3 times just so we can see how I'd rewrite this equation. This original equation is 1/4 x to the 4th plus x cubed plus 1/2 x squared plus x plus 1. Okay, then we need the first derivative. 4 comes down, multiplies by 1/4, so they cancel. We get x cubed plus 3x squared. I think I missed a squared here, so that's awkward. There we go. Plus x plus 1. And then we need our second derivative, the equation that tells us about concavity. 3x squared plus 6x plus 1. All right. This is the equation that we want to optimize. We want to find the largest or smallest in this case, right, most negative, the smallest concavity that occurs on this equation. Cool, that is my step 1. And although there's a derivative involved here, that's kind of irrelevant. There doesn't have to be a derivative, right? So they want to know what is the largest or smallest quantity, concavity, that occurs on this equation? And whenever you want the largest or smallest of an equation, your very first step is to take the derivative of that equation. We need to do step 2. We need to find the critical points of the equation we're trying to optimize. So although I'm going to call it f triple prime of x, really you should just think of it as this is the derivative of this equation. It doesn't matter if it's a third derivative, second derivative. This is the equation that finds critical points for that equation. All right, so what do we get? We get 6x plus 6, or factoring, we get 6 times x plus 1, I think. Cool. So then we want to find critical points, which means set this equation equal to 0, or we want to look where this equation does not exist. However, it's a polynomial. It exists everywhere. So let's go ahead and move on to setting this equal to 0. 6 times x plus 1 equals 0. So I think we end up getting x equals negative 1. All right, that's the only critical point. I'm proud of us. Now to the candidates test. As a reminder, the candidates test says, okay, we want to find either the largest or smallest value of f double prime. We found the critical point, and we'll also need some endpoints, which are these guys over here. And it's just going to be a plug and chug style game where we're going to say, okay, here is my input. The concavity value is the output, and we'll just need 3 of these because we're going -5, the critical point, and 5, those endpoints, yeah? And we just have to substitute them in here. So we have 3 times -5 squared plus 6 by -5 plus 1. Some mental math, 25 times 3 is 75. So we're looking at 75 minus 30 plus 1. I'd call that 76 minus 30, which I think is 46. All right, next one, we're substituting in -1. Looks something like this. Okay, -1 squared, 1 times 3 is 3, 3 minus 6 plus 1, I'm reading that as 4 minus 6, which is -2. And then last but not least, 5. This is going to be, I think, very similar to the top one, except there's going to be a plus instead of a minus in the middle, right? 75 plus 30 plus 1, so I'm seeing 105 plus 1, 106. What did we want? Well, we wanted the most negative concavity. That could occur at either the endpoints or the critical points. The most negative concavity is -2. Great. All right. Now, there's a second step 4 over here, this lonely critical point theorem in quotes, because it's not really a theorem, but it is referenced sometimes, and sometimes people can't keep straight. When do we use the candidates test versus when do we use the first derivative test? Well, let's remind you of the first derivative test. What the first derivative test is generally used for is finding the relative maxes and mins, right? Relative meaning if you had a graph that looked like this, the first derivative test would find these guys. But in this case of the graph I just drew, which I'm going to erase, none of those are the absolute max or min. This is the absolute min, this is the absolute max. So if I just said, ooh, critical point, I think that's it, you could totally be wrong because it could occur at the endpoints. Now, let's actually look at the first derivative test for this problem. So the first derivative uses, in this case I should be saying first derivative in quotes, it uses the derivative of the equation we're trying to optimize, and it looks at the signs of that derivative. So f triple prime, which is the derivative of f double prime, we're looking from -5 to 5, and there was one critical point which made f triple prime 0. We should test a couple points here, right? And I'm just going to test them into our equation over here. I'll use a different color. Equation up here, I think that's pretty easy. If I do something like -2 over here and substitute -2 in up there, you get a negative value. If we do anything larger than -1, like 0, you get a positive value. So what does this tell us? Well, this gives us the shape of the equation that this is the derivative for. It gives us the shape of f double prime. It tells us that f double prime will decrease and then increase. So if this is the graph, the general shape of f double prime, right? If I wanted to go through and graph f double prime, and we're not going to, but I just wanted to show you, it tells us that it goes down till somewhere and then back up somewhere else. And there would be actual curvature here, right? We don't really know how far, and I don't know why I wrote it like that. We don't really know how far, but there, we don't know how far down it goes, but there would be some curvature too. But this is still a general shape. And looking at that general shape, do you have an idea of where the smallest point is? I do. this point right here is the lowest point on the graph of f double prime. Therefore, that point there must be the absolute minimum, right? So just by looking at this sign chart, we can see that there are 3 points here. Two of them are two of them are large. One of these, of course, is going to be the absolute max. We don't know which one because we're not sure which one is higher, but we're very confident that this is both a relative min and an absolute min. And so because there's only one critical point here, it's very easy to tell that. And so what's sometimes done is as soon as you realize you're like, ooh, that's the smallest point, I don't want to plug something into all 3 of those. I'm just going to plug in the one critical point that I know. And we're going to do that one right now. F double prime of -1, we did it over here, is -2. Now, how do we conclude with this? Because the justification for the candidates test is really easy. You just evaluate every possible answer, or every possible x value that could create the absolute max or min. And once you have all the answers, you circle it, and you should probably draw an arrow up there and say, you know, absolute lowest or most negative concavity, right? Something like that. Here, though, we have to do a little bit more because just writing this doesn't explain how you know that that's the lowest because the reader isn't allowed to look at your sign chart. So instead, what we do is just a quick, we'll need, I think, 2 sentences here. First, we're going to explain that this point is a relative minimum, right? So as f triple prime of x changes, I should zoom in, sorry, changes from negative to positive at x equals -1, then x equals -1 is a relative minimum. All right. Second sentence. Now that we've given the relative min, now we're going to have to explain why this is an absolute min and also what the value is. Right? So second part, as, and I guess I'm starting as with both sentences with as, but judge me later, English teachers, as f double prime of -1 equals -2, and x equals -1 is the only critical point. And that's that lonely critical point here. We're not going to reference the lonely critical point theorem. The idea behind lonely is that there's only one critical point. You can even see that in there, right? There's only one critical point. If there's one critical point, you can do it this way. And x equals -1 is the only critical point. Then f double prime of -1 equals -2 is the absolute minimum for f double prime of x. That's the idea behind that lonely critical point. So it really comes down to you. What do you prefer to do? Do you want to do a lot of arithmetic and plug all of these in, right? You can. That's not too bad. It didn't take us too long. Or do you want to go straight to a sign chart if there's only one critical point and write 2 sentences? And I kind of alternate back and forth. It is good to know both. They do come up sometimes this way. But either way, up to you, and you can practice both today. I'll probably stick with the candidates test, but one way or another is fine by me. Okay, so the concept of optimization goes a bit further than just maximizing or minimizing a function, right? Although using the candidates test does still occur on the AP exam, optimization seldom does because honestly, optimization is pretty complex. It usually gives you, again, that one equation where it says find the largest salary you can make at this firm. But then it gives a whole bunch of extra equations, these extra constraints. And it says, but also remember that you have to pay this in taxes, and you also have to do this, and you also have to do that. And somehow you have to work all those into the original equation. And working those into the original equation actually has nothing to do with calculus. You generally cover it in pre-calculus. And the issue is if you make a mistake on the first step on how to combine all those constraints into a single equation, then you just automatically get the rest of the problem wrong, and you haven't actually done any calculus there. So they've really started removing a lot of these optimization problems from the AP exam, but the core idea is still very important. The core idea, again, being if you want to optimize, find a largest or smallest quantity for an equation, you start with the equation, you take the derivative, and you perform either the candidates test or, in some cases, if there's only one critical point, the lonely critical point theorem. So I have 4 problems that we're going to work through here. And actually, I would really like you guys to try to work through these, right? 1, 2, 3, and 4. The fourth one, you definitely need a calculator. It says calculator active. That doesn't mean calculator optional. It means you need a calculator. So I would like you to try them, and then you can either unpause after each problem or after all 4. Ready, set, go. All right, so hopefully we're back. Let's get to it. A lot of these are going to revolve around graphing, and these are all non-calculator active besides the last one. So let's see what we can do here. Find the area of the largest rectangle bounded by the x-axis that can be inscribed in the parabola y equals 9 minus x squared. Well, let's look at that. Okay, 9 minus x squared, I would prefer to write as negative x squared plus 9, because then we know it's up here at 9, and it's a parabola that's going downward, right, like so. We will also, for this, need to know, since this is bounded by the x-axis here, right, bounded by this guy, can't go below it, so I don't care about anything here. We're going to need to know where these x-intercepts are. So this is a nice reminder of how to find x-intercepts. We always set the y to 0 because we want to know the x value, right? Something like this, and we get x is plus minus 3. Cool. So 3 and negative 3. Now, what are they talking about with this rectangle inscribed? Let me give you a quick example, right? You could inscribe a rectangle like so. And I'm just going to pick a value. I'm going to say 2 and negative 2, right? For a rectangle, it's always going to be centered about 0, 0. So this distance and this distance are going to be the same. Looking at this then, let's actually find the area of this rectangle. I think that'll help us further down the road. So first thing we need to do is find the length of the base. And hopefully looking at it, you're like, well, that's 2 and that's 2, so the length of the base is 4. And you're 100% right. But we could also find the length of the base just by doubling this coordinate down here, couldn't we? 2 times 2, which is, of course, 4. Awesome. If we want to find the area here, because it doesn't say we want to find the area of the largest rectangle inscribed into this parabola, then I think we're going to need the height as well. So like, well, this is 2. How do we find the height? Well, the height is really along the y-axis. And remember, if we were to put a point here, and I learned how to erase better, put a point here, this is the point 2 comma something. And the 2 is, of course, the distance along the x, and the something is the distance along the y. And to find this something, we just take that 2 and plug it into our equation. 9 minus 4, this is 5. Which means then that the height is f of 2, which is 5. I think now we have enough to find the area. This area, to find it, right, we take the base, which is 4, times the height, which is 5, and we get an area of 20. Now that was one example of a rectangle. There are many others. If you set it at 1, you'd have a rectangle like so. Does that have a larger area? I don't know. If you set it out here, would this one be larger? I don't know. And so we're actually going to use calculus to determine what x coordinate will give us the largest area, and then actually we're going to go further and actually find the largest area. So let's begin. First thing we need to do is actually figure out the equation that we're trying to optimize. And this is a very similar setup to related rates, though we're skipping the rates part and we're jumping straight to the equation. This equation, of course, is the area. We are trying to optimize the area. So then the question becomes, how do we find the area of that rectangle? Well, jumping back over here, let's go through our steps. The first thing we had to do was figure out the base. And I think the base, isn't that just the x coordinate doubled, right? If the base was 2.5, then we double that to get a base of 5. Okay, so that's pretty easy to write once my screen zooms in, zooms out. I think my base here is going to be twice whatever the x coordinate is. But how do we find the height? Well, the height here was just found by taking that x coordinate and putting it in to the equation negative x squared plus 9. That gave us the height of 5. So that's not bad either. I think if I jump back over here and everything catches up, I think the height is just going to be negative x squared plus 9. And just a reminder for later on, this is the base times the height. Cool. I would suggest probably multiplying this out because our next step is going to be to take the derivative, but if I took the derivative, wouldn't that be a product rule? That kind of seems gross. Let's not do that. So distribute the 2x inside. We get negative 2x cubed plus 18x. Okay. And so we get to our second step, which is, of course, the derivative. Okay. The derivative, this isn't a DDT situation. We're trying to find the x value. We would just want to see, instead of thinking of it as dA dx, though that is what we're doing, we're doing ddx of each side, I actually like to just use the prime notation because I don't want you thinking of this as how something's changing as other things are changing. We're just thinking of the derivative. And I think that's a little bit easier in this situation. We're just saying to maximize or minimize an equation, we always take the derivative. And that is a pretty easy derivative to take, I think. We could even factor this a little bit further. Taking out a negative 6, I think, leaves us a 3 here. And now we're off to the races. Absolute maxes and mins can occur at critical points or end points. So let's look at our critical points, right? Critical points occur when the derivative is equal to 0 or the derivative does not exist. However, a prime exists everywhere. So we just end up with negative 6 times x squared minus 3 equal to 0. Divide off that 6 and begin solving. Look at that quick solution. We found 2x values. Okay, well, let's go ahead and actually, before we start setting up that candidates test, let's think about both the 2x values and what are our endpoints of this interval here. That's strange, right? So jumping back over, our square root of 3 is smaller than the square root of 4. Square root of 4 is 2. So square root of 3 is somewhere in here. Now, if I built a rectangle with a positive square root of 3 base, then the total base would be 2 square roots of 3. If I built a rectangle with a base of negative square root of 3, then the base would be, using our formula, it'd be negative 2 square roots of 3. You could, of course, say, well, let's just apply absolute value, and you could, but I think, honestly, you could really make the argument that the only x values you need to consider here are from 0 to 3. And you can make that argument in two ways. First, you could say, well, it doesn't make sense to use a negative x coordinate because then everything becomes negative and life gets weird. The second argument is that if you use a positive version, the negative version will create the same rectangle, so why do it twice? So I would argue then that our endpoints are 0 and 3, and our only critical point is the square root of 3. So let's get to it. Again, I'm going to go to that candidates test just to remind you, and I think it's more common to use the candidates test too. So our candidates test, and I don't put an apostrophe here. I'm not sure if that's right or not. I don't think it's their test. I think it is there are plural candidates and you are testing them. So I don't think we use an apostrophe at this point. Okay, so let's go ahead and get to it. We have x, and then we need to find the largest area. We had 3 values here, pretty common with this. 0, square root of 3, and 3. We're going to use our area formula. I'm going to use the factored one. 2 times 0 times, why am I doing the rest? This is just 0, isn't it? Okay, 3. 2 times 3, negative 3 squared plus 9. This is also 0, so that's 0. Cool. Square root of 3. Well, it's got to be this, I think. I think it has to be bigger than 0, right? So square root of 3. 2 times the square root of 3, negative square root of 3 squared, minus 9. Let's continue this guy out just a little bit to see what we get. 2 square roots of 3 times, let's see, this is 3, negative 3 minus 9. Oh, it's plus 9. I was like, that's a negative number. That doesn't make sense. Negative 3 plus 9 is 6. So I'm getting 12 square roots of 3. Nice. This is the largest area possible. Now again, you could have made a sign chart if you wanted using, and I'll show you really quickly, using a prime, 0 to 3, square root of 3, made a prime 0, and I already know what this is going to look like. If this is the largest area, then my graph's going to look like this, and you would have gotten a negative, nope, that's not how signs work. You would have gotten a positive and a negative, because this is both a relative max and, in this case, the absolute max. There's that lonely critical point theorem. Cool. So try again, try a few more. They're all kind of derivatives of this. But I think if you get stuck, you can totally unpause and see how we do it. Ready, steady, go. Alrighty, the point's 3, 0, that's right here, right? X, 0, that's right here. X, 1 over the square root of x, or the 1 over x squared, and 3, they didn't even put that one, that was rude. 3, 1 divided by x squared make up a rectangle where x is always greater than 3. So we know that this value here is always greater than or equal to 3. Well, in fact, if it was equal to 3, it would move all of this on top, and you just have a line with an area of 0, so that doesn't make a lot of sense. It's always to the right of 3, though. For what value of x does the rectangle have maximum area? Well, we'll do the same thing too, and you might notice this cute little pun here, area for work. We are going to start with our equation, and since they're asking us to maximize area, we're going to start with an equation for area of a rectangle, which is of course base times height. So how would we calculate the area of the base? I think the easiest way to do it is just to pick a value for x, right? The x can be anything, it varies, that's why it's a variable. So what if x was, say, I don't know, 5? Well, to find the area of this rectangle, you'd have to find the base first. From 3 to 5, that's a distance of 2, but since we're trying to generalize, how would you find 2? Wouldn't you do 5 minus 3, which is 2? Or since this is x, x minus 3 is going to give us the base here. So we end up with a base of whatever x is minus 3, and then we need a height. Well, let's see. If this is a base of 2, how do we find the height? Well, that's the distance up the y-axis, so we can just use the y-coordinate, which is the distance up the y-axis. So we just take this value and we plug it in. Oh, no, not that value. Sorry, we take 5. We take the x value and plug it in, right? This is the point 5, comma something. So whatever x is, we plug it in here to get 1 over x squared. And so actually that makes this pretty easy. This is just becomes 1 over x squared. Nice. There's our base times height. I'll clean it up just a little bit and write it as x minus 3 over x squared. You could clean it up further, but I figured this is a good excuse to practice the quotient rule because, of course, our next step is that derivative. So derivative-wise, we're going to say that a prime, the derivative of a, that'll help us maximize or minimize a, and quotient rule, 1 x squared minus, keep the top the same, 2x all over x squared squared. We should probably clean this up since eventually we'll be setting it equal to 0. X squared, and there's a minus here, so let's try to do 2 steps in one and not get our feet too much in muddy water here. So minus 2x squared, and then this is minus 6x, but there's already a minus, so I think it becomes plus 6x over x to the 4th. Continuing further, and I'll probably have to work sideways since I've run out of room, I get negative x squared plus 6x divided by x to the 4th, or factoring out an x, and I'll factor out a negative x. I like when that x squared is positive, so it becomes x minus 6, just double checking, yes, that looks good, over, and I'm going to treat this as x times x cubed, that's still x to the 4th, isn't it? Because now these cancel, and we end up with negative x minus 6 divided by x cubed. Yes, of course, you could distribute that negative back inside. All right, we've done that. We should probably find my critical points. Critical points. Critical points occur when a prime is 0 or a prime does not exist. I think there is actually a case where a prime does not exist, right? This is a fraction. Fractions do not exist when the denominator becomes 0, which means x equals 0. However, we're not going to test that critical point because they told us that x has to be greater than or equal to 3. If this was 0, then 0 would be over here. That'd be smaller than 3. It'd be a really confusing rectangle that got like warped around and shifted. So that one's out. Where is a prime 0? Well, that's when the numerator becomes 0. And you can bring the negative with you, but you really don't need it if you think about it, right? X is 6. 6 will cause the numerator to become 0, but then negative 0 if you want. All right, at this point, we have, I think, a few values to try. Okay, so trying these values is going to be a little bit interesting. So we have x, sorry, this is my last step here. We have x, and then we have our area as a product of x. Okay? And so my x's are, well, the smallest value x is allowed to be is 3. We got a critical point of 6. And then what's the end point here? For what value of x? Well, I think the end point, you would argue, is infinitely large, right? Couldn't we move this out infinitely large? And I bet you might even be able to see what happens when this is infinitely large. Now, the AP exam frowns upon plugging in infinity, and so on a free response, they'd probably have you do a little bit more. But this is more of a Calculus 2 concept, but we can do it here, nothing too bad. Let's say that this is going to be b, but it's going to be the limit as b approaches infinity. Because then that's a different way of saying infinity without actually writing infinity. And so the calculus exam really frowns upon plugging in infinity, using it as a number. So the workaround is to just use a letter that's going to infinity. That's not exactly infinity, it's just getting there. So again, that little workaround. So let's see what happens. If we substitute in 3 to my area equation up here, that gives me 3 minus 3 over 3 squared, which is 0. Okay, we'll tackle this limit as b approaches infinity. Substituting b in for the x's, b minus 3 over b squared. Oh, we're at infinity. We know how to do that. That's dominance, isn't it? And so for dominance, we're going to go ahead and say that instead of b minus 3, let's just use b. What difference is it? If you're at infinity, subtracting 3, negligible, right, over b squared. And continuing to simplify, this is 1 over b, right? And so this becomes 0. And again, this is not a shocker, because if you drew a point out at infinity, right, and then we had the graph that was right above it, we'll look at this silly little rectangle, right? Looks like that. And infinity would bring these 2 points infinitely close to each other, so you'd have a rectangle that's right on top of itself, which is an area of 0. Then we try 6. Okay, 6 minus 3 divided by 6 squared, that is 3 over 36, which is 1/12, which isn't a large rectangle either. However, since we have this 1 over x squared factor, it kind of ruins the area a bit. Of course, they didn't ask us what the actual area is. They said which value of x does the rectangle have a maximum area, and we found that that was 6. 2 to go. Consider a triangle in the xy plane. 2 vertices of the triangle are at 1, 0, and 5, 0. I should probably draw this. I think this will help me a little bit. It doesn't have to be perfect, but we'll do something like this. 1, 0, and 5, 0. Cool. And then a third vertex is on the graph of y equals natural log of 2x minus 1/2 x plus 5 for any x between 1/2. Oh my gosh, who designed this problem? Between 1/2 and 8. Okay, so if we put in 1/2 here, and I don't even know what we get for that. I think we'll have to try it eventually, but either way, actually, yeah, let's try the endpoints. I think that'll help me make the graph. Oh no, yeah, we might need them eventually. Let's try that. So let's see what happens if we find y of 1/2. Just for fun, right? We got some time. Natural log of 2 times 1/2 minus 1/2 times 1/2 plus 5. So this becomes natural log of 1 minus 1/4 plus 5. Natural log of 1 is 0. Any log of 1 is 0, right? That's one of our log facts we need to know. So I just have 5 minus 1/4. Isn't that 4 3/4? Yeah, I think so. 5 minus 1/4, 4 3/4. That looks good. Okay, what about y of 8? Y of 8. Well, looking at this guy, I think it becomes natural log of 2 times 8, right? Minus half of 8 plus 5. This is the natural log of 16, minus 4 plus 5. Natural log of 16. Well, let's look at these answers up here really quickly. I'm not sure we'll have to do anything like this, but I'm seeing a lot of values in front of the natural log. Let's just keep it as natural log of 16 plus 1 for now, and maybe we won't have to use any more log properties. Okay, so these are both positive values, right? Any log after 1, since log of 1 is 0, any log after that is going to be positive. Positive plus positive is a positive. This is 4 3/4, so somewhere up here. So we have a graph that starts here and kind of does its usual natural log thing and goes out over here. Cool. Technically, gets closer to this axis down here, something like that. I don't know, whatever. We have this graph. Now, getting back to the triangle, we already have, and I should draw this in a different color, we already have the base of the triangle. But how high does it go? Well, they're basically saying take every point that's on this graph from 1/2 to 8 and use each of those as different vertices for this triangle. So there would be one triangle. Here's another, and another, and another. And actually it looks kind of cool, right? But either way, there are lots of triangles. There are an infinite number of triangles, and they are asking us, what is the largest possible area of this triangle? Where the very last point would be over here, and the very first point, of course, would be over here. Whew, that's a lot. I'm probably going to need extra room here, just as a heads up, so if you want to get an extra piece of paper ready, not a bad idea. Let's start with the equation. They're asking us the maximum area of a triangle, so we better start with the area of a triangle. 1/2 times the base times the height. All right, well, how do we find the base of this triangle? I think the base is a constant, isn't it? The base is always this guy down below. Shouldn't use green, already used green. The base is this guy down below. 5 minus 1 is 4. The base is always 4. That's kind of nice. The height, though. Oh man, how do we do that? Well, I think the height of any triangle is always measured by taking one of the points and dropping what's called an altitude straight down to get a right angle. So the height of each of these triangles over here, if I wanted the height of this triangle, just drop it straight down. Couldn't we define the height as the distance from the x-axis up to the graph? Or instead of the distance, isn't that just the y coordinate of each of these points is going to be the height of the graph? Well, how do we find the y? Well, the y is equal to all of this. Oh, that's easy. So actually our height here is just this function natural log, and I should do this in parentheses. So we remember this whole thing is the height of 2x minus 1/2 x plus 5. And I'm actually definitely going to want to simplify that a little bit. Half of 4 is 2, so it becomes 2 of natural log 2x minus 1/2 x plus 5, or even further, let's distribute that 2 inside. We get 2 ln of 2x, ln of 2x, half of 2 is 1 plus 10. All right, there's my equation that will find the height for any x value of our triangle. On to the derivative. Here we go. We should probably do this. Okay, derivative a prime, which will help us maximize a. 2 is a constant, it's just going to hang. 1 over what's inside for the natural log, but wait, the chain rule, times the derivative of what's inside. Derivative of 2x is 2. Minus 1x becomes minus 1, 10 becomes 0. Okay, so I think we're really looking at 2 times 2, which is 4 over 2x minus 1. Or isn't this just 2 over x minus 1? I think it looks pretty good. Cool. All right, critical points. So where is a prime equal to 0, or where is a prime not exist? Well, a prime doesn't exist for an x of 0, clearly, right? If x is 0, then you're dividing by 0. That's a no-go. But they told us the x's had to be between 1/2 and 8, so there's no solution here. A prime equal to 0 means we're going to set 2 minus x minus 1 equal to 0. Probably add that 1 over to the other side. Multiply both sides by x, and we get 2 equals x. Critical point. Nice. Now, we could substitute in something into every equation, right? And actually, I already did most of the hard work over here. In fact, I should show you the candidates test. That would be silly not to. So let's look at the candidates test really quickly. The candidates test, and actually I kind of like this one for the candidates test because I already did this math on the other side. So the candidates test is just going to plug x's in here and then multiply them by 2. So we have our x value, we have endpoints of 1/2 and 8. All right, and then we found one critical point of 2, and this is our area. So 1/2, notice we already plugged 1/2 into the function and got 4 3/4, or if it makes you feel better, 16, 17, 18, 19 quarters, right? We do that around the world sort of thing. So 19 quarters here, and then we have to multiply by 2. So we have 2 times 19 quarters, which just becomes 19 halves, or what is that, 9.5? Yeah, 2 times 9 is 18. Cool, 9.5. 8, similar idea. We got this guy down here, natural log of 16 plus 1, and then we need to multiply that by 2. So 2 natural log of 16 plus 2. Nifty. Then we have our last one, which is just 2. And I actually haven't done that math yet, so I might as well do that. It's natural log of 2 times 2 minus half of 2 plus 5. Distributing the 2 gives me 2 ln of 4. Half of 2 is 1. 2 times 1 is 2. That's a negative, though, so minus 2 plus 5. And so we end up with 2 ln of 4, right, plus 3. Okay, well, looking at these 3, you might be a little stumped here, because you're like, well, wait, I don't remember a lot about logs. Is a smaller number better? Does this actually make it bigger? Or are these guys larger? I'm really not sure here, because I'm not great with logs, huh? Well, the other way we could have done this is after you find those 3, and you'll notice, I think, they are mostly all answers. Not all. We have 19 halves in the other one. I wonder if I made a mistake on this 2 natural log of 4. This was supposed to be 10, wasn't it? So 10 minus 2 is 8. I'm looking at those, and I'm like, I don't see an answer of a plus 3. There's that other answer. So all 3 of them are answers. Of course they are. Well, the way we could have done this faster is with that lonely critical point theorem here, where instead of doing all of this junk, and instead of plugging everything in, especially because these equations are complicated, what if you just looked at a quick sign chart? You said, I want to go from 1/2 to 8, 1 critical point at 2, and we want to just look at our derivative equation, which is actually a really nice, easy equation from something so complicated to start. For example, if I plug 1 into my derivative equation, 2 over 1 is 2 minus 1 is 1, that's a positive. And then if I plug in, let's say, 4, 2 fourths is 1/2, 1/2 minus 1 is a negative. This tells us that my equation increases and then decreases, yeah? Okay, and so they want the maximum area of the triangle. Okay, and to me, the maximum area is this guy, which is pretty surprising because you look at this and you're like, wait, natural log of 16, that's bigger than natural log of 4. And it is, but it's not that much bigger. So these are both small decimals. They're both small decimals. And then you have a small decimal plus 2 versus a small decimal plus 8. And so a small decimal plus 8 is actually going to be bigger than that and also bigger than 9.5. But we could have very quickly seen that visual by looking at the sign chart and saying, oh, these are small, this is a relative max, and because it's the only critical point, it has to be the absolute max. So then instead of trying all 3 of these, you could have just tried this guy and said, I already know that's the answer, so that has to be it. And so yeah, pretty counterintuitive there, especially looking at all 3 answers. Tricky, tricky question, but we were able to get through it. Last but not least, the graphing calculator active one. Given that the area under the curve of y equals cosine of x is 2 square units. Ooh, I should probably take a look at that over off on the side too. So just showing you really quickly, we have, yeah, we'll try to line it up, something like this. Cool. And then we have cosine, right? Cosine goes sound effects non-optional. And what they're telling us then is that the area right here is an area of 2, right? That's like our, if you shaded everything, the area is 2. Okay. Identify the minimum area of the shaded region if a rectangle with one side on the x-axis has upper vertices on the graph as shown in the picture. Whoa, Nelly. Okay, well, the first thing I think we'll have to do is come up with an equation that tells us how to find this shaded area. Well, actually, I think, well, there's a couple ways to do this. Yeah, let's try that and see where it leads. So equation-wise, I always start with some real numbers. We probably actually want to know where cosine crosses the x-axis, right? We know this is a point, of course, something comma 0. So what value can we plug into cosine to get 0? Hopefully you're saying pi over 2, pi over 2. This one's negative pi over 2, negative pi over 2. Because you're right, because cosine of pi over 2 is 0, which is why we have x-intercepts there. All right, so that's looking good so far. Yep. So then what do we do from here? Well, we need an equation. So again, mentioned, let's use some real values here. So pi over 2, 3 over 2 is like 1.5-ish, a little bit bigger than 1.5. So let's use, I don't know, 1. So if I called this 1 and this negative 1, how do we find what they're asking for? Well, I think the first thing to realize is that to find this whole area, we already know it, it's 2. But then to find just the outer piece, aren't we going to do 2 minus the rectangle in the middle, right? 2, and then we cut out this rectangle, and that leaves us with the shaded area. So I think what's going to happen is we're going to take the whole area, which is 2, and then we're going to subtract out the area of the rectangle. All right, this gives us a nice starting point. I should have said area equals. So that's really shaded area equals. So continuing through, 2 minus, well, how do we find the area of this weird rectangle thing? Well, let's start by talking about how we're going to find the total base length. I think we're just going to double this x-coordinate. Whatever the x-coordinate is, if it's 1, you double it, gives you a length of 2. If it was 0.5, you double it, gives you a length of 1. I think that's pretty easy. It's just 2 times whatever the x is. So filling this in, it's going to be the base, which is 2 times whatever the x-coordinate is. And then, of course, the height. Well, to get the height here, the height we've seen before is the y value. We already know the x is 1. To find the y, I think we have to plug that into the cosine equation, right? That gives us the point on cosine. Remember, we don't know what cosine of 1 is, so that makes it a little trickier here. But yeah, I think we're going to multiply by the height, which is just a friendly old cosine of x. Cool. And then, of course, the final area of this interior box will be 2 times 1 times the cosine of 1. Once we've found that, that's going to be some number. We subtract it from 2, and that's the area on the outside, which is what we've done. We found here the area for the shaded region. Our goal, of course, is to, what is our goal? I don't know. Identify the minimum area of the shaded region. Okay, so we want to find a way to make it the smallest area possible. Oh, that's right, because the biggest area possible would be so easy. The biggest area possible would be make a rectangle with an x-coordinate of 0. Well, your rectangle would just be on top of itself, which is an area of 0. And so the biggest area would just be 2, no rectangle. What's the smallest area? That is a tricky question. Let's clean up the area a little bit more by distributing that negative, and we get this guy. All right. Well, one way we could do this is, of course, actually find the derivative. I mean, that's a great way to go. So 0 minus, and actually I'm going to tell you this is minus 2 times these two guys. So minus 2, and the reason I'm separating that is because x is attached to cosine by multiplication, so we do need our product rule. 1 cosine of x plus x times, what's cosine? Negative sine of x. There we go. Nifty. And then we'll probably clean this up a little bit. So this becomes negative 2 distributed, so negative 2 cosine of x. And then there's already a negative here, so I think it's going to become plus 2x sine of x. All right. Then we need to find critical points, so that's where a prime equals 0 or a prime does not exist. But we're just dealing with compositions and combinations of continuous functions, which means they'll exist everywhere. A prime equals 0. I don't want to set that equal to 0 and solve. In fact, I'm not confident I know how to solve that set equal to 0. So what do we do? Well, this problem is calculator active for a reason. So let's get to it. In fact, I'll show you 2 different ways we could have used our calculator here. No matter what, though, you're going to need the graphing capabilities because we're looking for where a prime is 0. And this, of course, is an equation in its own right. So if this is an equation, we're going to graph the equation and find where the equation is 0. So negative 2 cosine of x, I'm going to probably forget this, but negative 2 cosine of x plus 2x times the sine of x. I always like to put an extra times in there because sometimes calculators, when you do x sine, notice how sine didn't actually turn into the usual sign, so cosine isn't italicized here, and this x sine all stayed in italics. This is actually going to cause an error on your calculator because you typed in the word xsin, and your calculator is staring at that going, what is xin? I don't know xin. And so you do need to separate when you have two letters next to each other that you're trying to show are two different words. And I'm going to put a times in the middle here and watch what happens to sign. Oh, there we go. Now we get the nice clean, crisp, non-italicized sign we were looking for. Double check my function's right. -2 cosine 2x sine of x. We've crushed it. Enter, graph, whatever sounds good to you. And we should get something like this. Now, I see a lot of zeros. 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros. And in fact, because sine is cyclical and cosine is cyclical, they repeat in cycles, I think that there's actually an infinite number. So do we list them all? Probably not. Remember, our original graph only goes from -pi/2 to pi/2. So I think we can probably change our window settings. So menu, window zoom, window settings. We're just going to go from -pi/2 to pi/2. I just typed out pi because I'm using a keyboard. Your pi key's down there, nothing bad, and enter. That's much nicer. And due to symmetry, I bet these are the same x-intercept. And in fact, one negative, one positive, of course. In fact, we really, in terms of our length of our interval, are only looking from 0 to pi/2 for the same reasoning as the first problem. If you use 1 over here, that's the same as using -1. It's the same rectangle. Everything becomes negative and weird. So we're really only looking from 0 to pi/2. So let's go ahead and find that one. Menu, analyze graph, 0. We've practiced this before. Here's this, but I don't trust it. I don't trust it at all. We need more. Look at all that. Okay, there is my 0. Now, a cool graphing calculator trick, and I'll show you this one on the 84 in a second too, but I'm going to show you something else on the 84, so we'll need both. Looking at this, we found the 0. I want to use this number later on because eventually we're going to have to find, right? It says identify the area. We're going to have to plug in that x value to my area equation. And so since I'm going to want to plug this in, I'm actually going to go through and save this value so I can use it later on. To save values on the Inspire, it's a little tricky, and it works the same way on pretty much every calculator. You're going to need to access the STO, the store function. We want to store this for later on. So you're going to want to run your finger lightly over the trackpad at the top of your calculator so you get your cursor moving around. You're going to move it over there, over the value you're interested in, and you're going to click one time. So clicking once. If you do that, it's going to highlight the number. Now, if you click on yours, it's kind of tough to tell. And the real issue I have here is if you click twice, watch what happens if I click a second time. That's not what you want. Notice now you can like edit the number and everything. I don't want that. And if you click too many times and you're not sure, just hit the escape button to bring you back out and try again. Just once. Should try clicking once better. Okay, just one time. There we go. And then once you've clicked one time, you need to access store, which is control and then var, because store is, of course, blue. If you did it right, it'll pop up like this, and it'll say define, this is our colon equals, means define what as this answer. And we're just going to pick a letter. What letter do I want to use? I want to use the letter A, because why not? And I'm going to hit enter. Now I have stored it. Notice if you roll over, it says it's linked this value to A. And so if I go back to my other screen, my calculate screen, and type in A right here, there's that value again. Super cool. You're like, but it only gave a couple decimals. Well, if you highlight it and hit enter, it actually stored as many decimals as possible. Now, I mentioned using the 84 as well, and on the 84, and this is an interesting idea, I wanted to give you a different way you could have done this problem. Because it's calculator active, notice that you didn't actually have to find the derivative by hand, did you? I think instead, couldn't we have just made the calculator graph the derivative of this? So, showing this here, if we have 2 minus, I said minus, oops, and I'm saving things. Trouble with the keyboard on this 84 emulator. So I have, second try, I have 2 minus 2x, and I always put the times in between x and cosine. I think it's a good habit to get into. 2 times the cosine of x, right? There's the original area equation. All right, and then jumping down here, if I just want to have this graph the derivative, we learned this last class, or 2 classes ago, didn't we? Math, derivative, and you can do this on the Inspire too, right? We put in the original equation. I'm going to take the derivative of my original equation, at x equals x. And then I'm going to change the window settings right away too. Let's just go from like -2 to 2. So I can be lazy here. And, oh, this isn't changed either, so let's go, I don't know, like -5 to 5. Sounds good. Let's take a look at the graph. Look at that. It's already going to graph this same equation that we have over here, except I didn't have to do any calculus. How cool is that? We made the calculator do the calculus. And we could have done that here too. I'll demonstrate really quickly. I am going to delete everything. I'm going to go back to it. And our original equation was 2 minus 2x times the cosine of x. Okay, and then I want to graph, right, quick key, I wanted to graph the derivative of f1 of x. Okay, and actually, I'm going to turn off f1 of x so we don't get too confused. And we have that. Ta-da! No calculus involved at all. I wonder if my a is still saved over here. I bet it is, but let's find out. So let's clear this. A, enter. Okay, it's still saved. Cool. So let's go ahead and find the same a on the 84. So that's our second calc 0. Move our little blinky, I always think of it as like a spider, a little bug, to the left of the intersection. Move it over to the right of the intersection. Find that 0. And it's about the same, right? 0.8603. Now, storing things on the 84 is actually a little different. So it just says x equals this. Well, what I'm going to do is I'm going to go back to the main screen, and I'm going to put x on the main screen. So alpha, and then x is way down here, or you could have just clicked the x button, doesn't matter. And if I hit enter, you'll notice it already stored it. But that's a temporary store, because as soon as the calculator uses x for another calculation, another graph, anything, it's going to change what that's stored as. So I always like to go through and restore this. So currently this is in the answer. So if you actually just do store right now, it's going to say previous answer, that's this guy, store it as what? And now I'll store it as a, just to stay consistent here. Right? And so that way, now that you've put it as any other variable besides x, it's going to keep this stored, and when you do different graphs and it replaces x with other things, it will not change this variable here. Okay, we found our critical point. Now we need to go back to our candidates test. Well, our candidates test is kind of silly. I think if you use 0 or if you use pi over 2, you're going to end up getting an area of 2 for both of them. We already really talked about it. If you don't believe me, you can plug them in. So really all we need to do is substitute in our value. And in fact, I didn't write the value here, so we should do that. And this is the cool part with our graphing calculators, right? If we have a prime equals to 0, all I'm going to do is say x is approximately 0. I've already forgotten what it was, 860. There's my approximate value, right? And they do ask you to go to 3 decimal places, so be careful. We don't want to stop with 0.86. It's always good to put the third one, even if it is 0, because that tells them that you know it's not exactly 0.86, 0.860, and even if you want, go an extra one. Nothing wrong with that. You can always put more. They just stop reading after the third one, but they would want to see that 0 there. They want to make sure you know to go to 3 places. All right, let's go ahead and find the area at that x value, 0.8603. Okay, and it's going to be what? Well, we have our calculators. We are awesome. And I know that my original equation's in f1, so let's just do f1 of my variable a. 0.8778. 0.8778. And you'll notice by a little bit of rounding, that is b. Of course, you could do that on the 84 as well if you want to clear out everything. Our original equation's in y1 of alpha a. Hopefully we'll get about the same thing. We do. Look at that. Very cool problem. Definitely tricky. However, using the calculator is a nice reminder. And that is it for today.